hope this marker works. Yay, marker! Well, hello and welcome to the Monday lecture. Today we're going to be discussing the machine design of the machines for the designing. So let's get started. Okay. So what we're going to be talking about this week is fatigue. We're in our 6th week of school. We all know fatigue, so stupid lecture, am I right? So when it comes to fatigue, fatigue is something completely dissimilar from anything else we've really faced before. We've talked about static failure. That was last week. In static failure, we know that if you take a bar and you bend it enough, eventually this bar is going to plastically deform. Give me a second. I'm going to exchange the batteries in my microphone right in front of you. So I will go silent for a second. But don't fear. It's all things happen. Oh, that worked. Nice. Oh, that was faster than I thought it was going to be. Dang, I was hoping to go for a lengthy expose where I just talk and the mic cuts out and it just like get really deep into the universe, but that didn't happen. So we know that if you could just bend this bar, eventually it's going to plastically deform. It's going to stay bent. Okay? This is awesome. Very useful. Static failure, okay? We also know that in more brittle materials, like say this was concrete, you bend this bar far enough, it will absolutely fracture. And you'll end up with concrete dust all over, okay? We got the brittle failure, we have ductile failure. We understand those concepts, that's what we talked about last week. Now, in this week, what we're gonna be discussing is what happens when we don't get anywhere near the failure limit and we still manage to fail. Okay? And this is ultimately what fatigue is. So the concept, the very principle behind fatigue is it is failure that occurs when a material or a component or some item undergoes repeated loading and unloading. Okay? So when you have a changing loading value, this is ultimately fatigue. Now there's a lot of materials that have been developed to be able to handle fatigue. Every building has to be able to handle fatigue. Certainly floors, because you walk across them so often. But things we don't think about that handle fatigue is, let's say you've got a vehicle axis, a vehicle axle, right? Driving down the roadway, you have constant load acting downward on this axle from your vehicle chassis. The vehicle has a weight. And when it acts on this axle, the issue is this is a constant downward load. But the axle itself, you know, if let's say I've got a black mark here that identifies at some point in the axle rotation. At this point here, that black mark is pointing upward. However, this force stays downward as this axle continues to turn. And what you have is that at its peak, this black mark will be in compression. Here on its side, it'll be in shear. When it's on its bottom, it may be in tension because of the bending load that's going on it. So we have to have a dynamic loading that is going on this axle, where every time it spins once, it experiences a brand new, what we're going to call a cycle. It goes all the way from being loaded one direction to being loaded the other direction, back to being loaded one direction. And axles experience a lot of cyclical loading like this. In the other lecture that we're going to give today, we're going to talk a little bit more about this. But ultimately, when it comes to fatigue, all fatigue is it is failure that happens when you repetitively load a material. Okay? Load, unload, load, unload. Now there are multiple different types of loading and unloading. As we're going to talk about I believe I'm going to wait till next week to even cover it. Fatigue is such a big concept. One type of loading is you have a harmonic loading like this, where you have a median loading. One type of loading is where you have completely opposite loading, where it goes from some value to the negative of that value and back. It doesn't necessarily have to be harmonic like this. This is the type of loading that we're going to be discussing today. But when it comes down to fatigue, this causes failure because if you remember a concept that I introduced to you a few weeks ago is that failure ultimately occurs because we assume that there are microscopic cracks in a material that grow. And as we load that material, those microscopic cracks, they begin to stretch. When we're doing this statically, meaning we're loading it once and that's it, we have a material like this, and let's say we have a crack like this. You load it once, what happens is, that crack will grow a little bit. Now if you release this, the crack stays, it's still broken there, but then when you load it again, you pull on it multiple times. Every time you pull on it, that crack is going to grow a little bit more, a little bit more, and a little bit more. And the more that this crack grows, the more likely it is, well, first of all, you have less area that's actually carrying this load. This load cannot be carried through this hole. There's nothing to carry that load. It just breaks there. The loading breaks. So all of the load is being carried on this side of the crack. Well, the more that crack grows, it means the more load has to be taken through a smaller area. Which means as this crack grows, eventually you're going to reach a point where there's too much load being carried here and it's just going to snap. Fatigue growth, failure can occur very rapidly. It has the pictures in the book that the pictures show is that fatigue failure can be a brittle form of failure where it just snaps. Fatigue can be, it experiences that kind of behavior, and it's kind of a phenomenon there because it's not something that you would see in static failure. It's only something that you see in fatigue. Different types of materials have different failure methods in fatigue, and even different types of fatigue loading will create different kinds of failure. So fatigue itself is kind of a broad field. What we're going to be talking about in the next lecture after this one is one approach to being able to calculate fatigue. And we'll get to that. For right now, we want to discuss the concept of cycles. Okay? So what is a cycle? Okay, if we have, let's say we've got an axle, and the axle spins all the way around. One revolution of that axle you're going to be experiencing some tension bending loading, nothing, compression bending loading, nothing, something like that. I guess that's actually, if the force is pushing downward on it, this would be in compression, this would be in tension, whatever. But as it spins around, it goes through a full cycle where the loading actually does look like this. It is harmonic. But it's centered around the very center line here, where this is completely reversed loading. What does completely reversed means? Well, it means that the amount of compression load it experiences here is identical to the amount of the tension load that experiences there. Okay, so this is completely reversed. And what you have for one cycle is ultimately from where it goes from one value completely reversed and then back to that same value. When it does that, that is one cycle. Okay, so we're going to define cycle as far as fatigue as one period of time by which a load is applied. We could say reversed and reapplied. Okay, and the reapplication at coming back to the same point is one cycle. So here, this distance from being fully in compression down here to being in tension to being back in compression, or this tension, compression, tension, I guess. Going from tension to compression back to tension, that is one cycle. So here this is one cycle, this would be another cycle. Okay, when it comes to fatigue, the number of cycles that a material experiences is very strongly linked to its overall quote-unquote strength. And here you deal with about two concepts. There are some materials like an axle, your vehicle axle, traveling 1 mile is something like 1,000 revolutions, or I guess not 1,000, but you know what, whatever. It's something like 1,000 revolutions of your tire. 1,000 revolutions of your tire means 1,000 cycles just to travel 1 mile. If your vehicle travels, if you have a 200,000 miles on your vehicle, it means your axle, in order to not fail, has to be able to withstand 2 million cycles. 200 million cycles. My apologies. 1,000 times that, because it has to rotate that many times, and that's not counting the number of times it has to back up. That's not counting the fact that you may go beyond 200,000 miles. So having an axle that can handle 200 million loading cycles of being put in compression, tension, compression, tension, that's really critical for the lifespan of your vehicle. And this is one thing that automotive agencies have to test. If they run a vehicle for 1 million miles and the axle fails because of all the cyclical loading it's experiencing, then they need to reinforce that axle. They need to redesign it. It's not good enough. The conditions that they put on it didn't work. If you're just driving down the roadway and all of a sudden your axle just ka-chunk, your car is not very good. Or you've experienced some very high cyclical loading, that could also be the case. At the end of the day, we have to design for the number of cycles because it is strongly correlated with the strength of a material. Okay? If you have a lot of cycles, your strength of your material is going to decrease. It's not going to be able to handle as much loading if you have higher cycles. So this brings about the concept of, okay, fatigue failure is determined by 1, you're loading. Oh, you know what? I'm gonna use stress. Stress magnitude. Okay, higher stresses, more likelihood of failure, right? That makes sense. That's the same concept when it comes to static failure. The higher the stress, the more likely your component is to fail. Okay, 2, material strength. We know this too. This was, again, the same for static failure. The stronger the material, the less likely it is to fail. Higher stresses, higher material strengths, that was kind of how we handled it. Oh, we have a certain amount of stress in a material. We could either pick a better material or we could redesign the component to have different geometries to be able to handle it. Okay, but beyond this, these were kind of the 2 biggest determining factors, is what stress, which is stress as a function of loading and geometry, and the material strength, which is a property of the actual material that's chosen. But we also have here in fatigue now, we have the number of cycles of loading that a material has to experience. But we also are going to be dealing with not just the number of cycles, but we're also dealing with how fast they're loading, you know, how often they're loading. What it looks like. If we're going up to some value and then dropping back down a little bit, and then going back up and dropping down, that is a cyclical loading, and that's not going to be anywhere near as bad as if we're going up to a certain value, going all the way down to the negative value, and all the way back up. Okay? That very large rise where it is completely reversed is the worst kind of fatigue loading. It is the harshest condition you can apply to a material. But if it's something where it's just like vibrating, like I'm sitting on the ground and I'm just vibrating a little bit, this is not producing as much fatigue loading as it would be as if I was jumping up and down off the ground and actually pulling on the ground on my way up. Now that is full fatigue loading, and that's a lot more dangerous. So knowing that we have these 4 principles that ultimately guide how we determine failure, we can come up with what's called the SN curve. S stands for strength, N stands for number of cycles. Okay, so all this shows is if we have S up here and we have N down here, which means, you know, if we're going to subject our component to 1 cycle, then that'd be over here on this curve. Now this is usually a logarithmic scale. And what that means is that you'll have 1, 10, 100, 1,000, 10,000, and it shows up where, you know, this would be 1, 2, 3, 4, 5. Well, it doesn't change a whole lot with that. Typically this is done in a logarithmic scale where this is 10 to the 0th, 10 to the 1st, 10 to the 2nd, 10 to the 3rd, that kind of a thing. Or they may use a base scale of 2 on their logarithmic scale. But ultimately this gives us a really broad range of what we're looking at. We can go up to 10 million without the whole graph just being shabba, which tells us almost nothing. Like, look, it's a straight line now. You know, if this wasn't a logarithmic scale, say we had, this was 0 and this was a 100,000 million. Or 100 million, 200 million, 300 million. Okay, if we wanted to get out to a billion, your graph would look like this. And this doesn't tell you a whole lot of information, unfortunately. So that's where the logarithmic scale tends to look better. Because in a logarithmic scale, you can see the differences in cycles between 1, 10, 100, 1,000, 10,000, 100,000, million, 10 million, etc., etc. Okay? And what you'll notice on this Oh, I thought my microphone was going to run out of juice. Apparently not. Noise! What you'll see is for 1 or 2 loads, your strength of your material is very, very close to your yield strength or your ultimate strength. Okay, the failure conditions here at very, very low loads are close to your SY if it's a ductile material, or your SUT if it's a brittle material. Okay, so really close to 1. It starts to decrease. You start to notice that there is a decrease. That your material isn't able to handle 10 cycles the same way it handles 1 or 2 or 3. Fully load, remove that load, fully load again. Okay, so at 10 you see a little bit of a decline. At 100, it starts looking like this. At 1,000, you start seeing a little bit less of a decline. At 10,000, well, according to the material, 10,000 isn't a whole lot different than 1,000. And then ironically, all right, I'm going to replace. Guess that's what I get for buying trash batteries. Hopefully that solves the problem, because now my pack is now blue and everything is a-okie dokie again. Hopefully. So what we have here is the difference between 1,000 loads and 10,000 loads. The way that a material sees it actually isn't that big. Like for us, 1,000 to 10,000 is huge, but not that big of a deal. The material behavior tends to be a lot more. And what you'll see is after about 10,000, 100,000, a million, after about this point, it experiences what the book calls a knee. And what that is that the strength never actually reduces beyond that value ever again. Okay, so you're at a knee, where now it's done. At very low loads, your strength of your material can handle up to your yield strength or your ultimate strength. At very, very high cycles, your material can handle some just suddenly plateaus, where now it can handle some strength no matter how many loads you put on it. And this principle for this SN curve, it can be really helpful, because if you want to design something to have an infinite lifespan, you want to design it to be somewhere with this strength value here, where you know no matter how many loads, how many billions and billions of loads, you're always going to be able to handle that amount of strength. When car manufacturers create axles, they determine this value by cyclically loading an axle repeatedly. And once they've found what that strength value is, then they can use it for all of their axles. And that's all it takes. They know where this plateau happens. They know where this knee occurs, where you have an infinite number of cycles that a material can handle at this load. Okay? Now, I'm going to go ahead and say this is for steel. This is not for aluminum. Aluminum's graph, if we were to, let me say, I'm going to redraw this SN curve now, where this is going to be 1, 10, 100, 1,000, 10,000, 100,000, million, 10 million, 100 million, billion, 10 billion, 100 billion, trillion, 10 trillion, 1T, 1B, 1M, 1K. Okay, Okay, if we're looking at this for steel, steel looks something like this. Oop. Where it's usually about 10 to the 4th to 10 to the 6th cycles where it reaches its plateau. This is steel. For aluminum, if you can find an aluminum that has the same SY value, what happens is aluminum does this. Aluminum never reaches a plateau. In fact, the higher the loading cycles that aluminum experiences, the lower the stress value it is. You can make aluminum fail by loading it with higher cycles. That's it. Any aluminum component, you can make it fail with just more cycles. Now, we're dealing in the trillions of cycles here. Okay, we're talking about a very, very, very long time before it fails, but this is still true. This is why they have to decommission airplanes, because eventually these aluminum components are going to fail. They can't help it. That's how it is. You're going to replace those components. The aluminum themselves, they can't last forever. They do not have an infinite lifespan, whereas steel components do. So when we talked about materials at the beginning of class and I said steel is better at handling fatigue, this is why. Because aluminum, if you design for it to have 1 billion cycles, you can figure out what this value is and you can say, that's my strength. But other than that, I mean, you want to go 1,000,001 cycles, it fails. Whereas steel, you say I want it to go 1 billion cycles, well that's the same value as a trillion, as a quadrillion. Because it has that knee, it has that malleability inside of it where it can handle crack propagation. When crack stops propagating at some point. In aluminum, the cracks continue propagating indefinitely. Okay, I'm going to go ahead and jump to the next lecture where we're going to be talking about endurance limit. A little bit more on this concept of endurance limit and how it values strength. So